Alright, hi guys. In this video, we are going to talk about the chemistry of carbon compounds. Basically, another topic of organic chemistry. And today we will focus on the isomerism. So let's get started. Now, first of all, isomerism. What does it mean by that? It's a new term. So it will be best if we explain it from the Chinese version. So the Chinese version of it is this one. Okay. Now, the first two words means the same molecular formula, right? Same molecule. So same molecular formula. But this one, different structure. Different structure. So we are trying to say that for some organic compound, actually a lot of organic compounds, they actually have the same molecular formula, meaning that they are made up of the same number of atoms, same types of atoms, but they occur in different structure. Okay, so let me just give you a very simple example. For C4H10, okay, C4H10, this is a molecular formula of an alkane, right? Now, you may say that, oh, this is a butane. Well, yes, it can represent a butane with all the carbons connected into a straight chain, all right? So this is one possible structure, okay? However, you may realize that C4H10 can also represent a compound like this, right? So this one is a methylpropane, right? So you can see both of these organic compounds have the same molecular formula, okay? Same molecular formula. However, they have different structures, okay? This one, the longest carbon chain is 4. This one, the longest carbon chain is 3. So they have different structures. Even the name is different, right? So this is what we call isomerism. Okay? So let's check out those keywords regarding isomerisms. So isomerism occurs when two or more compounds, usually organic compound, have the same molecular formula, okay? Same molecular formula, but different arrangement of atoms, or different structures, if you put it, different structures, okay? Or there is another situation where we will talk about it later. They have different spatial arrangement of atoms. Now this one, we will talk about it later, okay? What do you mean by spatial arrangement of atoms or groups of atoms? And if this falls into the first, if your isomerism falls into the first category, we call those structural isomerism. And the other one, if it is related to the spatial arrangement of atoms, then that would be referred to as the stereoisomerism. Now, sounds very complicated, right? With many, many new terms. Now, let's look at this kind of a diagram that shows you, okay? Now, isomerism, like I said, same molecular formula, but different structures, or different, representing different arrangement of atoms. So if the difference is related to the structure, then we will call it structural isomerism. If the structure is the same, but there is some difference in the arrangement of atoms in the three-dimensional space, then we will call this one stereoisomerism. Now, at this moment, you still may not understand what you mean by three-dimensional arrangement. Let's say this one is related to the structures and this one is not related to the structure, okay? So now, if they have a difference in structure, we can subdivide it into three types. So chain isomerism, position isomerism, and functional group isomerism, okay? All these three belongs to structural isomerism. It all has to do with the different structures, okay? Now, let's take it slow. I will break it down for you one by one, okay? Now, one more thing. So isomers, they have different structures and even functional group, and therefore they could have different physical properties or even different chemical properties. As we go through this topic, this chapter, we will see sometimes isomers could have different physical properties, and even they may react differently. Okay, so we will look at it as we move on. Now, okay, let's focus on the structural isomerism. Okay, so again, different arrangement of atoms, okay, or different structures basically. Now, the first one is chain isomerism. Actually, this one is the one that I just showed you. This one belongs to chain isomerism. So for chain isomerism, the key focus is that they have different carbon skeletons. They have different carbon skeletons. What do you mean by different carbon skeletons? In other words, they have different longest carbon chain. Okay? Alright, that means different carbon skeletons. Now, let's look at this example. C5H12 is a 5-carbon alkane, but this molecular formula can represent 3 structural isomers or 3 chain isomers. This one is a pentane. So pentane, the longest carbon chain is 5, right? Now this one, 2-methylbutane or just methylbutane, you see the longest carbon chain has only 4 carbons. Whereas this one, 2,2-dimethylpropane or simply dimethylpropane, the longest carbon chain is only 3 carbons. So when the isomers differ from each other by the longest carbon chain, then these isomers exhibit chain isomerisms. Okay? So this is the difference. This is the idea. Okay? Now, these are some discussion related to the physical property. Like I said, different isomers could have different physical properties and chemical properties. In this case, if you look at these 3 isomers, they actually have different boiling points. You see, pentane has the highest boiling point, whereas dimethylpropane is having the lowest boiling point. And why is that? Now, whenever we come across physical properties in organic chemistry, we need to focus on the intermolecular force. Because, like I said, all the organic compounds are having simple molecular structures. So all the physical property boils down to the intermolecular force. So for alkane, you know they are nonpolar, right? No matter how the structures are, they are nonpolar. So what we are focusing on is the van der Waals force. Van der Waals force. Van der Waals force, usually we look at their molecular size or number of electrons, right? And the bigger the size, the stronger the van der Waals force. However, since they are isomers, meaning that they have the same molecular formula, meaning that they have the same molecular size, then how can we do the comparison? Same size, these are same size. Then how can we explain? Now remember, when we talk about van der Waals force, there are 3 factors altogether that determines the strength of van der Waals force. The first one is obviously the molecular size. The second one is the polarity. Polar molecules usually have a higher, stronger van der Waals forces. But there is a third factor, which is the shape of the molecule. The shape of the molecule. In this case, they all nonpolar. They all have the same size. So we must focus on the molecular shape. The shape. Okay. Now you see, despite having the same molecular size, the strength of intermolecular force are different. This is because of the shape. You see, pentane has a linear shape, whereas 2,2-dimethylpropane has the most spherical shape. Okay, so linear versus spherical shape. Okay, so the surface area of contact among the pentane molecules are larger than that of 2,2-dimethylpropane. Okay, so we talk about the surface area of contact for forming the van der Waals forces, and therefore you see the intermolecular van der Waals forces among pentane molecules is the strongest among the 3. accounting for the highest boiling point. And that is also true vice versa for dimethylpropane. Okay? So that explains the difference in physical properties among chain isomers. Okay? Now, the other one, the other type of structural isomer is position isomerism. In this case, if you look at these two examples, the difference would be the position of the bromo group. The position of the bromo group. So now you notice this time, they both have the same longest carbon chain or the same carbon skeleton. Both of them, okay, has 3 carbons being the longest carbon chain. So this one is not considered as the chain isomerism. Instead, this one is called position isomerism. Okay? So here, they have the same carbon skeleton and functional group, but their functional group are located at different position. Okay? It could be the functional group, it can as well be a side group. Okay? So that makes the difference. Okay? Now, sometimes some students may kind of mix up the chain isomerism and position isomerism. One way to verify is to look at the name. This one bromopropane. Here, 2 bromopropane. You see the last word, the suffix is propane, right? So that means they have the same longest carbon chain. However, if you look at these, okay, this one is pentane, this one is butane, this one is propane. So the suffix is different, meaning that the longest carbon chain is also different. So this is one way to double check, to verify whether it belongs to chain isomerism or position isomerism. Okay? Now, moving on to the functional group isomerism. This one could be the easiest, could be the most difficult. The most easiest because it's quite easy to identify if they are given, if the structures are given, because the different functional group is usually quite obvious. So for example here, C2H6O can represent ethanol and methoxymethane. So obviously the functional group is pretty much different from one another. Okay? C3H6O, in this case, it could be an aldehyde, it could be a ketone, it could also be something weird with a double bond and a hydroxyl group. Okay? So obviously they have different functional group. Pay extra attention to aldehyde and ketone. These two are quite similar, and sometimes students may mistaken it as position isomerism. Some people may think, oh, first position, second position, so it's position isomerism. But you realized the functional group is actually different. Okay? And this one, C3H6O2, with 2 oxygens, very likely it would be a carboxylic acid or an ester. So it turns out it could be a propanoic acid, it could be a methyl ethanoate, or it could also be ethyl methanoate. You know, you can always have different methyl group and different alcohol and different carboxylic acid forming the esters. Okay, well that we didn't talk about it, but you know. Anyway, so it could also be something weird like this one, which is a hydroxy group together with an aldehyde. Yeah, that could also be possible. Okay. So this is the functional group isomerism. Okay. Now let's do some practice. We have practice 1, 2, 3. Now let's do the first one. Okay. Let's quickly do the first one. Pause the video and then we'll talk about the first one, and then I will need to talk a little bit more for question 2, and then you will do the practice yourself. Okay, so pause the video and do question 1 first. Okay, so let's check the answers. Here, they all have structural isomerism, so the problem is which one. Okay, now here, this one, you see this one having a CO double bond at the 2nd carbon, and this one is at the 3rd carbon, so this one has to be position isomerism. Now I do not put down isomerism, but you know in the real exam you should put down isomerism as well. But you know, okay. This is because both of them are ketone, so it is not a functional group isomerism. Okay, for this one, so here the Cl, one is over here, one is over here. Then again, you may think about, oh, is it position isomerism? As a matter of fact, it is not, because these two already two different functional group, Here we have a chiral group and a carboxyl group, but here this is not a carboxyl group. This is something that you haven't learned. This is acyl chloride. We call it acyl chloride. Okay, but anyway, at least you should be able to tell me that there is a carboxyl group where there is no carboxyl group here. So that one must be a functional group. Functional group isomerism. Okay. Okay, this one. So both of them are alcohol, but this one has 4 carbon longest carbon chain. This one has only 3. So this one I will put it as chain isomerism. Okay, chain isomerism. Okay, both hydroxyl group is at the second position, if you realize. Okay, so it is not position. This one, they have the same longest carbon chain, but the double bond is in different position. This one is at the first position. This one is at the second position. So this one must be a position isomerism. Okay, so that's that. Now for question 2. Now you are asked to draw all the possible structural isomers. Okay, so is there any technique to do this? Yes, it does. We have a couple of tricks that can be used. So, but I want you to try first. Okay, I want to try first. But I can give you a hint. Okay, so for the first one, we could have 2 isomers. Okay, 2 isomers. For the second one, we could have 4 isomers in total. Okay, just try your best to figure out what are the possible isomers. For this one, I think there is altogether 1, 2, 3, 3, I guess. Okay, I could be wrong, but at least I can see 3 of them. And this one could be complicated. This one I can see, I'm not sure of 5 or 6. Okay, you guys have to figure it out. Okay, 5 or 6. Okay, when I just look at it, I can't really for sure. Even for me, I need to work it out. Okay, now pause the video and try. Okay, try. Okay, let's check the answers. Now the first one, this one is easy. This one, now I try to make it simpler. I don't put down the H's, I just put down the carbon. Okay, I don't want it to be too messy because obviously we don't have enough space here. So we can have a straight chain. We can also have brown chain like this. So you plug in all the H's. Okay. Now the second one, if you are smart, you know it is an alkene, right? Because it fits the CnH2n, the general formula. So there must be a CC double bond. So you should be able to identify at least this one, okay, a bu1-ene. And when we have bu1-ene, we may as well have bu2-ene. And we may also have a methylpropene. So I think for most of you, you should be able to get these 3, which is already very good. But what about the hidden one, or the other one? So this one, in fact, does not have any double bond, but it has a ring. Yes, so it could exist as a cyclic compound. If you find out the number of hydrogen atoms, it turns out that it is also a hydrogen atom. So you realize that forming a ring also require 2 hydrogen atoms lost from the corresponding alkane. Now, what I'm trying to say is, because if you remember from my last video, I tried to deduce the general formula of alkene. I said that if you want to form a CC double bond, you need to sacrifice 2 hydrogen atoms. Okay? So that's why from alkane to alkene, the general formula is from CnH2n plus 2, and then for alkene is CnH2n. Because 2 hydrogen atoms must be sacrificed in order to form a CC double bond. But not only does sacrificing 2 hydrogen atoms forming a CC double bond, but it can also use to form a ring, okay? To form a ring. So this one is the 4th possible isomers. Now this one, C3H8O. Now if you are smart, you realize that there is no double bonds. If there is no double bond, it is easier. It could be a propane 1O. When we have propane 1O, we may as well have propane 2O. And we can also have an ether, okay? Ether. All right, so these are the 3 possible products, okay? Now, for D here, I think this is quite complicated. It's more like a mathematic question. So, a better way of doing this is actually to find yourself a paper, and we try to do something in mathematics called tree diagram. Okay? So, here, C3H5Cl3. So you need to think about where the Cl should be put. Okay? So we start with, okay, a straight chain, because for 3 carbons it has to be a straight chain, right? So we do not have to focus on the hydrogen, we focus on the chlorine. Okay? So there are 3 possible positions for the first chlorine. Alright, so the first chlorine, I'll use the red to represent. The first chlorine could be here, okay, could be here, could be here, right? Do you agree? And then the second chlorine. The second chlorine could be put again in either position. So it could be again in 1, 2, 3. Okay, 3 different positions. So actually you do the similar thing for the rest. So you see it's sort of complicated. But no, this is the most secure way of doing this. Okay, Cl, okay, like here. Okay, what I do is the 1, 2, 3. I always place the Cl 1, 2, 3. Okay, now here we also do the same thing. Okay, the red Cl here. And we put down all of these things. Cl, and then for the second chlorine, again 1, 2, 3 position. So now we have 9 possibilities. Okay, now here. Because if I want to repeat these steps again, then I will have 9 times 3, so 27. That is quite a lot. But actually, at this moment, we can actually cancel out some possibilities. Okay, because some is already the same as the other one. Okay, so we can try to cancel out, for example, these 2. You see, these 2 are essentially the same, right? These 2 are essentially the same. So I can cancel out just one of them, so I cancel out this one. Okay? And then you realize this 2 is also the same, right? This 2 is also the same. So I can cancel out this one. And then you also check to see this 2 is actually the same. This 2 is actually the same. So I will cancel out this one. Okay? And then you also see that these 2 are actually the same, right? These two are actually the same, so I can cancel out this one. So now, what we have left, also these two are the same, you realize. This one and this one are the same, so I can cancel out this one, okay? So now, it will be easier for us to continue, because now we only got like 4 left. So again, we do the same thing. Now, we need to plug in our last chlorine atom, okay? So here, Cl, 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 okay, Cl, 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 okay? Now, the second one, okay, not enough space, huh? So I'll continue. Okay, this one, and the last one. You can't put another chlorine here because it does not have enough bond. So actually only here, and this one cannot exist. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 possibilities. Then what we are doing right now is to cancel out anything that is repeating itself. Okay? So let's see. Is there anything repeating? So here and here, these two are the same. If you realize, these two are the same. 1 Cl at the first carbon and 2 Cl at the second carbon. So I can cancel out this one. Okay? And this is also the same. This one. Also 1 Cl at the first carbon and 2 Cls at the second carbon. This one you can cancel it out. This one as well. This one is actually the same. Okay? And then 1 Cl at the first carbon, 2 Cls at the second carbon. Okay? Then these two are the same, these two are the same. Okay? These two are the same as well. Okay, so a final check. Actually, there are, yeah, I think that should be it. So we have 1, 2, 3, 4, 5, 6 altogether, 6. Okay, so you see, it's quite difficult. Okay, it could be quite complicated. Okay, now so let me put it down. So it turns out to be 6 of them. Okay, so it could be C, 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 Cl, Cl, Cl. It could be C, 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 Cl, Cl, Cl. It could be C, 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 Cl, Cl, Cl. It could be this one. Lastly, it could be. Actually, these two are the same, right? These two are the same, right? So only 5 of them. Only 5 of them. So that's it. Okay? 5 of them only. Okay, so I'm sure there are some mathematical method to solve this type of questions. but I'm not good at math, so I will do the traditional way. But don't worry, in DSC, I don't think they will have questions like this or that complicated one. Probably they will take away 1 CL, so you don't have to do that much, you don't have to handle that much of a possibility. Okay? Now, let's look at practice question 3. So here we have 3 alkanes, and then first of all, state the physical states of 3 alkanes in room temperature. Now you see that boiling points are all below 25 degrees Celsius, so that they are all gas. Okay, they are all gas. Okay. Physical states will be gaseous states. Okay. Name compound X, so this one should be methyl propane. All right. Explain the difference in boiling point between propane and alkane X. So, you see, propane and alkane X, this one is easy because they have different number of carbons. So, you can simply, by looking at the size, so here I just put down brief remarks. So, the molecular size. So, X is bigger than propane. So, therefore, the van der Waals force, okay, among molecules, okay, X will be stronger than propane. Okay, so just like that. Okay, now alkane X and butane exhibit isomerism. So state the type of isomerism exhibit between alkane X and butane. So alkane X and butane, they exhibit chain isomerism, right? Chain isomerism. Okay? Actually, if you're smart, you can also say structural isomerism. Because now the question didn't specify the type of structural isomerism. Now, so pay attention, guys. If the question is like this, state the type of isomerism, then you can answer structural isomerism or the specific type of structural isomerism. Okay? But if the question specifies, okay, state the type of structural isomerism, then you must state chain isomerism. Okay? Now, D2 is a very similar question as C here. So why do they have different boiling points? Now, this time, you can't make use of molecular size because they have the same molecular formula. They are made up of the same number of atoms. So their size are the same. So in this case, X versus butane, we will make use of the shape of the molecule. So we will say, first of all, we try to compare the molecular shape. Okay, so we say butane has a linear shape. Okay, whereas X has a spherical shape. Okay, then we will talk about so that the surface area of contact. So butane has a greater surface area of contact. Okay, so therefore, the van der Waals force among molecules, butane will be having a stronger van der Waals force than X, and therefore explaining the difference in boiling point. Okay, so that's the idea. That's the idea. All right. Now let's move on to the stereoisomerism. The stereoisomerism. Okay. So here, this is the part that could be quite problematic when teaching. All right. Yeah. Anyway, I'll try my best. So here, now, first of all, stereoisomerism refers to the spatial arrangement. So now, in this case, they have the same structure. So you see, the isomers, which their atoms are joined in the same order, meaning that same structure. same structure. However, the atoms or the groups of atoms have different spatial arrangement. By spatial arrangement, it means how the atoms are located in the three-dimensional space. So are the atoms located at one side, or they are located at opposite side, or from a three-dimensional perspective, is that atom pointing towards you or pointing away from you, and does that difference actually make a difference? So now we will break it down to you one by one. So, but you have this mindset, okay? We are talking about same structure. It's a matter of how the atoms or groups of atoms are located. Okay, the difference in locations. Okay. Now, first of all, the first one is called cis-trans isomerism, and the other one is called enantiomerism. These two are two different types of stereoisomerism. Okay. So let's look at this situation. Now, this one is a 1,2-dichloroethane. 1,2-dichloroethane. Now, there are two representations, and sometimes we did use different representation. But does it matter? Does it matter? Is this one equal to this one? Well, yes, it does. Now, why is that? It is because now let me just use. I don't have two green ball pens, so I'll make use of two blue ball pens to represent the chlorine. Okay. So you see, think about this black ball pen is representing the CC bond. Okay, it's representing the CC bond. And then the two blue ball pen is representing the chlorine atom. Okay, so now if I look at this one, then it looks like this, right? Let me kind of make it bigger. So now, if we look at this one, then it looks like the carbon, okay, carbon bond, and the two chlorine atoms is pointing upwards. Now the thing is, for the CC single bond, it can rotate. It can rotate. We can have a rotation here. Okay? So look at it carefully. You see the rotation. Okay, so now this one with two chlorine atoms pointing in opposite direction, which would be this one. Okay? So now you see these two are the same because the rotation is permissible. The rotation is possible. The atom can feel free to rotate its CC single bond so that this one and this one will occur at any time, at any given moment. Both of them can, either one of these can occur. So these two are the same compound because the conversion is permissible. Okay? So this is the idea. They are the same molecules. Let me magnify it again. Okay? They are the same molecules because of the unrestricted bond rotation. Unrestricted, that means feel free, okay, free bond rotation about the CC single bond, okay, which allows interchange between the two conformations. Okay, these two are what we say two conformations. So it allows the interchange of the two conformations. Okay. Now this is from the three-dimensional perspective because actually this one should be a three-dimensional molecules. So to represent this one is not too difficult. We can again make use of the blue ball pen. Let me figure out. Okay, it takes some time. So please wait while I try to grab all those pens on my hand. But don't worry, I did practice this before, so it should not be a huge problem. Okay, so let me step forward to you. So you see, now this one, you can consider this one as the same as this one. The two chlorine, the blue ball pen representing two chlorine atoms. Okay, so now they are pointing upwards. And the other two black ball pens, they are pointing into you and out of the paper. Now again, the rotation is permissible. So now, if we do the bond rotation 90 degree, then you will see, okay, for example, this one. Okay, now one of the blue ball pen is pointing away from you after the 90 degree rotation, right? Pointing away from you, the blue ball pen. Okay. Now you can see the blue ball pen on my right hand side. Now you don't. Why? Because it is pointing away from you, so that's why you can't see it. Now, what about another 90-degree rotation? Okay, that would be like this. That would be like this. Again, now because I have to move my body, otherwise I can't rotate my hands. So now, you see, the blue ball pen, now you can see it again. But now, it is pointing down. It is pointing down. So the two blue ball pen, one is up, one is down. That is actually the same molecule as this one. It just depends on the rotation. Okay, so this one and this is the same. Okay. Whew. So that's the idea. That's the idea. So in this case, we don't have any cis-trans isomerism because these two are the same. For isomer, we are talking about same molecular formula but different structure or spatial arrangement. But in fact, they do have the same spatial arrangement. They can always interchange by the bond rotation. So these two are essentially the same. So when we draw the structure, we can draw either one of these. It doesn't matter. And these two are the same simply because the bond rotation is unrestricted. Okay? So single bond allows rotation. Okay? However, what about this? Now this one, bond rotation is not allowed. Okay? So we see we have restricted bond rotation. Now again, let me show you. So this time we have double bonds, right? Double bonds. It's just like two, okay, blue ball pen, black ball pen. Now we have the chlorine pointing up, the two chlorine atoms pointing up, and then the two hydrogen atom pointing down, just like this, right? Okay. Now let me hold it onto my hand. Okay, so just like that. Okay, just like that. Now, okay, so now with the two chlorine atoms pointing up, now let's try to do a rotation. Now you see what happens when I do the rotation. Watch very carefully. What happens to the black ball pen in the middle when I do rotation? It kind of cross, right? It kind of cross one another, right? Just simply it can't do a rotation. Okay, otherwise I'll have to break the black ball pen. Okay, so you see a double bond. Does it allow rotation? No, it does not allow rotation. Okay, single bond does, but double bond, or even you can tell if it is a triple bond, bond rotation is not allowed. So that means if at the first place the two blue ball pen is pointing up, can they point it down? No, it cannot. If the blue ball pen wants to point downwards, they need to break it, okay, and then reform it, okay, like this. Okay? We need to break it and reform it. But if they have to break the bond in order to change the conformation, then that would be a chemical reaction, right? Then that would be something else. So in other words, this one and this one is two different compounds because they are not allowed to interchange from one another. And why they are not allowed to change from one another is because of the restricted bond rotation due to the CC double bond. Okay? So that's the idea. So over here, the restricted bond rotation about the CC double bond does not allow interchange between the two configurations. Okay? So here, it cannot rotate into this one. It can't rotate into this one. Okay? So if you look at this one, it's a three-dimensional diagram. Okay? When you rotate it, you see the bond kind of twisted to the point. And you can expect if it turns even more, the bond will be twisted and then will be broken. Okay? So this one is not possible. Okay? Now, so this is what we call the cis-trans isomerism. So pay attention to the terms. So cis-trans isomerism occurs when there are two isomers that arises from the restriction of bond rotation. Okay? And that has to do with the CC double bond or something similar. Okay? And cis-trans isomerism, this is an old term. if you look at the old textbook or old syllabus, we call it the geometrical isomerism, because geometrical has to do with the location, pointing up, pointing down, okay? Now, how do we distinguish them? So usually we focus on a CC double bond, and we focus on the large bulky groups, of substituents, okay, substituents. And we try to look at whether these bulky groups are on the same side or on the opposite side. So if this is on the same side, then we call it a cis isomer. So here, same size, then it is cis. Okay? If they are opposite side, then it is called trans. Okay? So usually I would think about it this way, because this one, you know, on the same side, so it looks like a C, right? It looks like a C. Okay, so cis. Okay? This one is a trans. Okay? Now when it comes to the naming, so these two, you see, they have the same name because they have the same structure, same arrangement of atoms, right? So they must be the same in terms of the name, right? 1,2-dichloroethene. But in order to distinguish them from the name, we will add cis and trans prefix at the front. Okay? Just like here, we have cis-butene and trans-butene. Okay? So here, the large group will be the methyl group. Okay? Now, it only happens when you have two bulky groups and the other two are obviously smaller groups. Like if you have something like this one, do you have a cis-trans isomerism? No, it doesn't, because no matter this Cl is pointing to the top or to the bottom, it is the same compound, okay? Because of that Cl here. Obviously, if this one becomes another Cl, you must not have a cis-trans isomerism, okay? So that's the idea. This is for reference only, so I'll just quickly talk about it. Restriction of double bonds not only occur at a CC double bond, but it also occurs in small cyclic compounds with a ring. Just like here, we have a 4-carbon ring, okay? So with the bromine atoms at the 1 and the 3rd position, so it can occur in a cis-trans fraction. Now think about it. So we have a ring. We have a ring like this, okay? And we can have the bromine groups either pointing to the top or one pointing down, okay? I don't know how should I put it, one pointing down, okay, underneath my paper. So if they are pointing at the same direction, then it looks like a C over here, right? So this one is a cis, and this one down here would be a trans, okay? And there is restricted bond rotation because think about it, if you have the whole thing here, it's difficult to hold it. Like this, okay, like this. If you want to rotate it, it's quite difficult to rotate. And as you rotate it, you see the bond angles also twisted. It's also kind of twisted where you have a acute angle and obtuse angle. And you know, what is it, obtuse angle? Doesn't matter, but the acute angle is such a small bond angle that brings the bonding electrons so close to each other, that repulsion between the bonding electrons will tend to destabilize the ring and eventually break it. So this is the reason why a small ring does not allow bond rotation. Okay? Okay, so you see the bond angle kind of twisted, and for those two angles become very small, it's very unstable. Okay, we call it a bond strain. Okay, but this one is out of syllabus, so only for reference. Okay, now here there are some interesting examples related to the physical properties, related to cis-trans isomers. Now, you realize that for cis-trans isomer, they may have different shape according to where they put the large bulky groups. So for this one, okay, butyl-in, we have cis and trans. Now you notice, if you look at the shape, I try to use maybe this one. Here, the electron cloud, if you think about the electron cloud would be sort of like this, like a C or like a V shape, okay? So it's more like spherical. But this one, the electron cloud, now I try to omit the hydrogen atom because hydrogen atom is very small. So the number of electrons contributed to the electron cloud by the hydrogen atom is not much. So I kind of omit it. So if you focus on the larger groups, you see the electron cloud, this one is more like a spherical shape, but this one is more like a linear shape. So when it comes to the melting point, where we're looking at their packing efficiency, so the trans-butyl-in has a higher melting point. You see, it has a higher melting point, okay? Because of a better packing efficiency, okay? So we focus on the shape, okay? Trans has a higher melting point because they have a higher packing efficiency, okay? Now for the boiling point difference, the difference is not much, so we don't talk about it, we don't focus that too much, okay? Now for the case 2, here we have polar substituent. Now, so you see here, these are non-polar, right? But here we have polar substituents. So in this case, we focus on the net dipole, or the polarity of the molecules. Now here in the cis isomer with 2 chlorine atoms pointing at the same direction, that results in a net dipole. Okay, so the molecules is polar. But this one, the dipole moment cancel out, or this is a symmetrical molecule, therefore the molecule is non-polar. So that one would affect their boiling point, and also that will affect their boiling point. So you see the cis-1,2 dichloroethene is having a higher boiling point simply because of being polar. Okay, so they have a stronger van der Waals force. You may see it is a different story for melting point. For melting point, the non-polar trans isomer is actually having a higher melting point. This is a situation where the packing efficiency of the linear shaped molecules outweighed the polarity. Now, because remember, for a melting point, not only do we look at the polarity, but we also look at the packing efficiency. So for this one, a linear shape packs more closely with one another. That factor in this case outweighed the polar cis isomer. Okay, so that's the idea. Okay, but I don't think they would ask you to explain the difference in melting point, because with these two contradicting factors, it's quite difficult for you to deduce. Okay. Now let's move on to the next one. Now this one is another interesting example where it's a very specific special case, I would say. So here we have butene dioic acid. So basically like a butene, but the 2 alkyl groups are both carboxyl groups. So here you see the melting point are hugely different from one another. Okay. Now you may say, hey, sir, this one cis, right? Polar side group, so should be polar. This one on opposite side, non-polar. So shouldn't it be this one having a higher melting point than this one? But it turns out that this one has a much higher melting point. Now it turns out that there is a very interesting situation where when the 2 carboxyl groups are on the same side, they will form the hydrogen bond between the 2 carboxyl groups. So this one is what we call an intramolecular hydrogen bond. So usually we say intermolecular hydrogen bond because the forces is in between 2 molecules, right? But here, if you watch it closely, the hydrogen bond takes place or occurs within 1 molecule, right? The hydrogen bond forms within 1 molecule between the 2 carboxyl groups. So it is not intermolecular force, it is intramolecular force. Now, so if this happens, then it will actually reduce the number of intermolecular hydrogen bond, right? So in other words, the formation of intramolecular hydrogen bond will greatly reduce the number of intermolecular hydrogen bond a cis isomer can form. This is the reason why the cis isomer is having a much lower melting point. Okay, it has less extensive hydrogen bond when compared to the trans isomer. Okay, so that's the idea. Now these are the three examples, cases. I think in DSC they will ask this one or this one. Okay, the boiling point, not the melting point. I don't think they will ask case 3. Or if they ask you the case 3, they should give you substantial information because this is a very specific case. Okay, special case. All right. Now we have a practice question with the cis-trans isomer. Again, pause the video, attempt it, and then we will check the answers together. Okay, so let's have a look. C2H2F2 can represent several organic compounds. Identify all compounds that have the molecular formula C2H2F2. Okay, so this one, if you are smart, you realize that there is a CC double bond. There has to be. So the CC double bond you can have, okay, the 2 fluorine atoms putting at the same position. You can have the fluorine atoms put in a different carbon. But when you put it into different carbon, that also gives rise to 2 different cis-trans isomers. Okay? So altogether 3 possible structures. Okay? Cis-trans and this one. Now this one does not have a cis-trans because the 2 large group is on the same carbon. Okay? Now here, among your answers in part A, 2 compounds are isomers of, it should be stereoisomer of one another because they are all isomers of one another, right? So 2 compounds are stereoisomer of one another. So state the type of stereoisomer, stereoisomerism. So this one must be cis-trans isomerism. Okay, and then state the systematic name of both isomers. So for this one, this is a cis 1,2-difluoroethene. Okay, and the other one, opposite direction. This one will be trans, and the name is the same, 1,2-difluoroethene. Okay? Right? Okay. So what structural features in the compound allow such isomerism to exist? Explain briefly your answer. So this one talks about the origin of the formation of cis-trans isomerism. So you will say that the CC double bond, okay, this is the structural feature, no, restrict bond rotation about the CC double bond. Okay? Alright, so that's the idea. Okay, explain the difference in boiling point between the 2 isomers. So this one versus this one. So now, boiling point, and in this case, you should have the cis isomer having the higher boiling point. So the cis isomer has a higher melting point. Boiling point, okay, because, okay, cis isomer is polar, while trans isomer is non-polar. Okay, so the van der Waals force among molecules, cis is stronger than trans. Okay, so that's the idea. Okay, all right. So that's that. Now, I think I will stop the video here because I think it already been an hour and 20 minutes and even more. So I will stop it here, and next video we will be talking about enantiomerism. Okay? So stay tuned and goodbye.